In this module, we are shifting our focus from simply writing programs that work to designing programs that work efficiently. As data grows larger, the choices we make about algorithms become increasingly important. In this module, we will explore how to analyze algorithm performance using Big O notation and apply those ideas to two foundational searching techniques: linear search and binary search. By the end of this module, you will understand not only how these algorithms work, but when and why one should be chosen over the other. When working with small datasets, nearly any algorithm seems fast. However, as data grows, inefficient algorithms can quickly become unusable. Algorithm analysis helps us predict how a program will behave as input size increases. This allows developers to avoid performance bottlenecks before they become serious problems. In real systems like databases, search engines, and operating systems, algorithm efficiency directly affects responsiveness and reliability. A program that produces the correct output is only part of the story. Two programs can solve the same problem correctly but perform very differently. With small datasets, those differences may be invisible. With large datasets, they become critical. Algorithm analysis gives us a way to compare solutions objectively and choose designs that will continue to perform well as requirements grow. Big O notation describes how the cost of an algorithm grows relative to the size of its input, usually represented as n. It does not measure exact execution time. Instead, it focuses on growth trends. This abstraction allows us to compare algorithms regardless of hardware, programming language, or implementation details. Software engineers should be concerned about efficiency, because a program that works correctly can still fail in real-world use if it becomes too slow or consumes too many resources as data grows. Many programs are developed and tested with small inputs, but production systems often handle thousands or millions of items, where inefficient algorithms quickly become a problem. Poor efficiency can lead to slow response times, frustrated users, and higher operational costs due to increased CPU, memory, or server usage. In some cases, inefficient code can prevent features from being feasible at all, especially in systems that require real-time performance. Understanding efficiency allows programmers to design solutions that scale, make better use of limited resources, and remain reliable as workloads increase. When using Big O notation, we intentionally ignore constants and lower-order terms. For example, an algorithm that performs 5 times as many operations as another may still be considered equivalent if both grow at the same rate. This may feel counterintuitive at first, but it allows us to focus on what truly matters as data scales. These are the most common time complexities you will encounter. Constant time algorithms always take the same amount of work. Linear time algorithms grow directly with input size. Logarithmic algorithms grow very slowly and are extremely efficient. Quadratic algorithms grow quickly and become impractical for large inputs. Understanding these categories helps you quickly evaluate algorithm choices. One of the most important takeaways from algorithm analysis is how dramatically growth rates differ over time. An algorithm that seems acceptable with small inputs can become unusable as data increases. Logarithmic algorithms, on the other hand, remain efficient even with massive datasets. This is why understanding growth behavior is more important than measuring exact speed. A linear search, also called a sequential search, is a simple method for finding a value in a list by checking each element one at a time from beginning to end. It starts at the first item, compares it to the target, and if it does not match, moves to the next item and repeats this process until the target is found or the list ends. Linear search works on both sorted and unsorted data, which makes it flexible and easy to implement, but it can become slow as the list grows because it may need to examine many elements. In the worst case, it checks every item, giving it a big O n time complexity, while it typically uses only constant extra memory. Linear search is the simplest searching technique. It checks each element in a list one by one until the target is found or the list ends. It does not require the data to be sorted, which makes it very flexible. However, this simplicity comes at a cost when datasets grow large. In the best case, linear search finds the target immediately. In the worst case, it must examine every element. As a result, its time complexity is O of n. This means performance degrades steadily as data size increases. While linear search is fine for small datasets, it does not scale well. Despite its inefficiency, linear search is still useful. If the dataset is small, unsorted, or searched only once, the simplicity of linear search may outweigh the cost of sorting or implementing more complex algorithms. Algorithm choice is always context-dependent. A binary search is an efficient method for finding a value in a list by repeatedly dividing the search range in half. It begins by checking the middle element of a sorted list and comparing it to the target value. If the middle element matches, the search is complete. If the target is smaller, the search continues in the left half, and if the target is larger, it continues in the right half. This halving process repeats until the target is found or the remaining range becomes empty, indicating the value is not present. Because binary search eliminates half of the remaining elements with each comparison, it runs in big O log n time, making it much faster than linear search for large datasets. The binary search requires the data to be sorted and typically uses only constant extra memory when implemented iteratively. Binary search has a logarithmic time complexity. Each comparison eliminates half of the remaining data. This makes it extremely efficient, even for very large datasets. For example, searching 1 million elements requires only about 20 comparisons. Linear search and binary search both solve the same problem, finding an item in a collection, but they are chosen based on the situation and the data. Linear search checks each element one by one and works on any list, including unsorted data, which makes it simple and flexible, especially for small datasets or one-time searches. However, it can be slow for large collections because it may need to examine every item, giving it ON time complexity. Binary search is much faster, running in O log n time by repeatedly halving the search range, but it only works when the data is already sorted. Because sorting can take time, binary search is usually the better choice when the dataset is large and will be searched many times, while linear search may be the better choice when the data is unsorted, small, or when the overhead of sorting is not worth it. The key lesson from this module is that algorithm choice has a real impact on performance. Big O notation gives you a way to reason about scalability, and searching algorithms provide a clear example of how different approaches lead to dramatically different outcomes. In this module, read the pages and experiment with the examples to get an idea of the code and purpose of each approach. Thanks for following along. We will see you in the next video.